Hello, my name is Ahmed Habib and I will discuss about light from the cosmos. So let's move to slide 2. First of all, we have visible light. Visible light is a type of electromagnetic radiation that can be detected by the nerves in our eyes. Modern astronomers study electromagnetic radiation, not just visible light, but other types as well, because examining this radiation helps astronomers to understand the composition, size, temperature, and movement of celestial objects. Therefore, to provide a foundation for discussing these objects, let's review the characteristics of electromagnetic radiation and consider how radiation interacts with the Earth atmosphere. So let's move to slide 3. Now, let's talk about the electromagnetic spectrum. Revisited. Well, electromagnetic radiation travels across space in the form of electromagnetic waves, which unlike sound or water waves can move through a vacuum. We distinguish among different types of electromagnetic waves by specifying their wavelength or their frequency. So let's move to slide 4. Electromagnetic radiation occur in a vast range of wavelengths, the entire range of which constitutes the electromagnetic spectrum. Visible light constitutes in a small part of this spectrum. Radio waves, microwaves, and infrared radiation have longer wavelengths than visible light, whereas ultraviolet light, X-rays, and gamma rays have shorter wavelengths. The amount of energy carried by electromagnetic waves depends on the frequency of the waves. High frequency waves carry more energy than the lower frequency waves. The way electromagnetic radiation interacts with the atoms, radiation must be pictured not only as a succession of waves, but also as a stream of particles. These particles are known as photons. Photons have no mass. Each photon contains a very specific amount of energy determined by the wavelength of the radiation. Let's move to slide 5. On the atmospheric windows, astronomers can determine many characteristics of a radiation source, be it a star, planet, or nebula, by analyzing the spectrum that the source emits. If all wavelengths of electromagnetic radiation could pass through the atmosphere, we will not need to send up satellites to study the heavens. Unfortunately, for ground-based astronomers, gas molecules in the atmosphere absorb most wavelengths of electromagnetic radiation. There are only two atmospheric windows, meaning ranges of wavelength that can pass through air without being absorbed. We have optical window. It's transparent to visible light and translucent to infrared energy. This means that nearly all visible light waves penetrate the atmosphere, but only some infrared radiation does. Next is the radio window. Radio window is a transparent to radio waves with wavelength between 1 cm and 10 meters. We refer to the study of visible wavelength as optical astronomy and study of radio wavelength as radio astronomy. And these different parts of spectrum can be observed with optical telescopes and radio telescopes, respectively. As we'll see, space telescopes can detect other wavelengths of radiation, such as X-rays and gamma rays that can pass through the atmospheric windows. Let's move to slide 6. As you all know, different wavelengths of light refract by slightly different amounts as they pass through the prism. Astronomers use spectroscopes, sophisticated prisms that spread incoming electromagnetic radiation into a very broad spectrum to analyze the radiation from stars. Let's move to slide 8. If you look closely at an image by a spectroscope, you'll see that the light from celestial object does not contain all possible wavelengths, but rather displays distinct spectral lines. Emission lines show up as narrow bright bands in the spectrum. Each emission line corresponds to wavelength of the energy emitted by specific element within a radiation source. When this happens, the spectrum display dark bands called absorption lines. At a specific wavelength, astronomers can use absorption lines for example, to determine the chemical composition of nebulae between a star and the Earth. So let's move to slide 9. Electromagnetic waves can undergo a Doppler shift when emitted by objects. Moving toward or away from an observer, the faster the object travels, the greater Doppler shift is. A shift toward a higher frequency happens when the object moves towards the observer, whereas a shift toward a lower frequency happens the object moves away from the observer. Therefore, a light source moving toward an observer exhibits blue shift, whereas a light source moving from an observer exhibits a red shift. So let's move to slide 10. According to the laws of blackbody radiation, the wavelengths at which a glowing object emits the greatest amount of energy depends on the surface temperature of the object. Hotter objects emit shorter wavelength of light, while cooler objects emit longer wavelength of light. By using these concepts, astronomers have determined that blue stars have a surface temperature of 20,000 degrees Celsius, yellow stars have surface temperature of 6,000 degrees Celsius, and the red stars have a surface temperature of 3,000 degrees Celsius. So let's move to slide 11. The size of a star is determined in a way that astronomers define it by giving its radius as a multiple or as a fraction of our sun's radius. Modern telescopes are sensitive to allow direct measurement of the sizes of a few nearby stars using special techniques by the help of telescopes. That's all. Thank you.